The James Webb Space Telescope JWST has revealed an extraordinary phenomenon: beams of illumination emanating from a distant urban area located light years away. This revelation has reignited discussions about the possible existence of extraterrestrial civilizations. The telescope focused its observations on Proxima Centauri b, the closest known exoplanet to our solar system, and detected unusual intense bursts of light. Could these emissions be evidence of an advanced alien society? Stay tuned for further updates. For years, both scientists and the general public have been captivated by the idea of life beyond Earth. Any indication of extraterrestrial life has been met with great enthusiasm. A significant breakthrough occurred when the JWST provided compelling evidence suggesting the presence of life elsewhere in the universe. While examining the vast expanse of space, this powerful instrument uncovered something remarkable on a distant exoplanet. Lights resembling those from human-made cities, raising the possibility that an alien metropolis exists on that faraway world. This discovery has generated considerable excitement and curiosity within the scientific community, as it could represent the breakthrough they have long anticipated. It suggests the presence of intelligent beings operating civilizations in ways we are just beginning to understand. Observing these city-like lights from an astonishing distance of 4 light-years away, NASA engineers are astounded, pondering how long they might have been visible in space, awaiting our technological advancement to detect them. David Kipping, an astronomer at Columbia University, has described the planet where these lights were observed as particularly intricate. Unlike most rocky planets that absorb sunlight and emit energy as infrared radiation, this exoplanet behaves differently due to its unique relationship with its host star Proxima Centauri. This discovery underscores JWST's critical role. Its capability to capture infrared wavelengths was essential in identifying the unusual behavior of Proxima Centauri b, which is crucial for understanding the planet's atmospheric conditions. Researchers plan to continue utilizing the telescope to study the atmosphere of this planet in greater detail, hoping to determine its potential habitability. The JWST is particularly adept at detecting infrared light, enabling it to observe phenomena on Proxima Centauri b. Even during the night, many telescopes struggle to detect faint light in the vast darkness of space, but the JWST excels at picking up even the faintest glimmers. This makes it an ideal tool to confirm if the alleged city lights on the dark side of Proxima Centauri b are indeed real. The telescope can detect artificial light in space, provided it falls within a very specific frequency range, much narrower than the light emitted by regular stars. Proxima Centauri b exhibits a dynamic interaction with its star, heavily influencing its environment. Like many planets that orbit stars, it captures intense energy from Proxima Centauri. As the planet revolves around the star, it undergoes cycles of day and night. Much like Earth, the planet experiences scorching heat during the day and cooler temperatures at night. The range of temperatures on Proxima Centauri b is vast, primarily due to its composition. For example, if the planet has an atmosphere, the temperature difference between day and night would be extreme: hot on one side and frigid on the other. This dramatic thermal fluctuation is a key area of interest for astronomers, as it provides valuable clues about Proxima Centauri b's atmospheric makeup. The JWST, with its ability to image in the infrared spectrum, can effectively examine the planet's thermal emissions, offering insights into its atmospheric properties. Interestingly, the orbit of the JWST around Earth coincides with the orbital period of Proxima Centauri b, enabling scientists to make detailed observations of its daylight cycles every 11.2 Earth days. If Proxima Centauri b possesses an atmosphere. The next step will be to analyze its chemical composition to determine if it could support life. Detecting elements like oxygen, water, vapor, and methane would suggest the planet's potential to harbor life. This would involve studying the light passing through the planet's atmosphere, a complex process. While the JWST is excellent for characterizing planetary atmospheres, it is primarily designed for other tasks. Its expertise lies in analyzing the concentrations of water, vapor, carbon dioxide, and methane, but it is less adept at detecting free oxygen, a crucial sign of life. Nonetheless, the telescope can search for other key indicators like ozone, which signals a healthy atmosphere. As scientists examine the data gathered from the JWST, the hunt for distant worlds continues. The search is bringing us ever closer to answering the question of whether we are alone in the universe. It's important to note that the JWST can only observe a limited number of exoplanets closest to Earth. For more detailed studies of planetary atmospheres, astronomers will rely on ground-based observatories like the Extremely Large Telescope (ELT), which is set to begin operations in 2027. The ELT is designed to offer a deeper look at the atmospheric structures of far-off exoplanets, providing clearer and more detailed data on their potential to support life. Scientists are eagerly awaiting the launch of future space telescopes like the ELT. In the meantime, the JWST remains an invaluable tool for exploring distant exoplanets. Despite its limitations, the JWST continues to offer critical information that may change our understanding of what exists beyond our solar system. Researchers have ambitious plans for future space telescopes. They aim to develop technologies that reduce starlight interference, allowing for better observation of the planets around them, similar to using your hand to block the sun in order to see more clearly. These upcoming telescopes will be able to focus on the faint light reflected by exoplanets, making it easier to analyze their atmospheres and assess whether they might be capable of supporting life. However, this task is far from simple. Stars are incredibly bright, often vastly outshining their surrounding planets. This brightness makes it difficult to detect the faint light that planets reflect, which is essential for studying their characteristics. To address this challenge, scientists are working on several innovative techniques. One such method involves the use of coronagraphs, devices placed inside telescopes to block out starlight while letting the light from the planet pass through. By carefully shaping the light waves, coronagraphs can significantly reduce the brightness from the star, making it easier to detect the dim light from exoplanets. Another promising approach is the Star Shade, a massive flower-shaped spacecraft that will fly information with a telescope positioned tens of thousands of kilometers away. The Star Shade blocks starlight before it even enters the telescope, allowing only the light from exoplanets to reach the instruments. This technique could be particularly effective in observing planets within the habitable zone of their stars where liquid water and possibly life could exist. However, these advanced technologies require extraordinary precision. For instance, the alignment of a star shade must be perfect to fractions of a millimeter over vast distances. Moreover, these innovations must overcome the limitations posed by space missions, including the need for miniaturization, energy efficiency, and the ability to withstand the harsh conditions of space. Despite these obstacles, the potential rewards are enormous. Successfully observing and analyzing the atmospheres of exoplanets could lead to the discovery of signatures, chemical indicators of life, such as oxygen, methane, or water vapor in specific ratios. These molecules might point to biological processes suggesting that life exists beyond Earth. Researchers are also exploring ways to directly image distant worlds in greater detail. Future telescopes could be equipped with advanced adaptive optics, which adjust for distortions caused by Earth's atmosphere or the telescope's movements, resulting in sharper images. Combined with starlight blocking technologies, these improvements could allow scientists not only to detect exoplanets but also to map their surfaces and study their climates. The development of next-generation space telescopes represents a significant leap forward in our quest to answer one of humanity's most profound questions: are we alone in the universe? By enhancing our ability to observe these distant planets, we are getting closer to finding out if life exists beyond Earth, potentially transforming our understanding of our place in the cosmos. The future of space exploration and the search for life beyond Earth is advancing at an unprecedented pace as scientists and astronomers delve deeper into the mysteries of distant exoplanets. The JWST is ushering in a new era of cosmic discovery. The data it gathers is helping astronomers make groundbreaking revelations about the structure, composition, and potential habitability of far-off worlds. With each new piece of information, we edge closer to the ultimate question: is there life beyond our planet? The discovery of Proxima Centauri b is just the beginning of what could become a major turning point in how we approach the study of extraterrestrial life. Proxima Centauri b, being the closest star to our own solar system, has been a focus of intense research for years. However, until now, finding concrete evidence of life such as artificial light or signs of civilization was a dream for many scientists. The fact that such light has been detected by the JWST only enhances the hope that one day we may contact other intelligent life forms in the universe. This kind of discovery fuels both scientific curiosity and public imagination, inspiring new generations to think beyond the confines of Earth. As the JWST continues its observations, it's not only looking for artificial lights, but also focusing on planet atmospheres, their chemical compositions, and how these factors could support life. The search for biosignatures like methane or carbon dioxide in the right concentrations is vital for understanding whether these planets have the right conditions for life. The JWST has the ability to examine these atmospheric components in a way no other telescope has been able to, shedding light on the potential of distant worlds to support life similar to Earth. One of the most fascinating aspects of Proxima Centauri b is its location within the habitable zone of its star, where conditions might be right for liquid water to exist on its surface. The habitable zone is the region around a star where temperatures are just right, not too hot and not too cold for liquid water to form. This is considered a critical factor in determining whether a planet could harbor life. Water is essential for life as we know it, making the discovery of an exoplanet within a star's habitable zone a key target for future missions. In addition to finding life supporting planets, future space telescopes will also be focusing on the complex relationship between exoplanets and their stars. Some planets like Proxima Centauri b are tidally locked, meaning one side always faces the star, while the other side remains in darkness. This can create extreme temperature differences between the two sides of the planet, which would affect the planet's climate and its potential to support life. Understanding these conditions is critical for astronomers as they assess the likelihood of habitable environments on exoplanets. The development of technologies that can block out the bright light from stars is another major step forward in space exploration. Without the ability to block out starlight, it would be virtually impossible to observe the faint glimmers of light from distant planets. The coronagraph and star shade technologies mentioned earlier are prime examples of how scientists are tackling this challenge by obstructing the overpowering brightness of a host star. These tools allow telescopes to detect the faint light reflected from orbiting planets. This light can contain vital information about a planet's surface, conditions, atmospheric composition, and even its capacity to host life. An especially thrilling advancement in this realm is the concept of direct exoplanet imaging through the use of advanced adaptive optics and light-suppressing instruments. Astronomers hope to capture high-definition images of planets as they orbit their parent stars. These images could not only reveal further insight into a planet's atmospheric properties and chemical makeup, but also show features like bodies of water, land masses, or large-scale weather systems, offering humanity an unprecedented look at distant worlds. Such capabilities would mark a substantial breakthrough in our exploration of habitable exoplanets and dramatically improve our understanding of their viability to sustain life. As the global effort to explore the cosmos intensifies, the James Webb Space Telescope JWST, along with upcoming missions, will play a crucial role. The JWST's proficiency in detecting faint energy signatures, dissecting atmospheric components, and evaluating potential biosignatures is transforming modern astrophysics. As technology advances and scientific understanding grows, we inch ever closer to revelations that could completely redefine our understanding of life in the universe. The accelerating progress in space exploration and astrobiology is creating opportunities never before imagined. Researchers and astronomers are continuing to dive deeper into the cosmic unknown, with the JWST leading the charge into a bold new era of discovery. The treasure trove of data it provides is already enabling astronomers to draw groundbreaking conclusions about the structure, chemistry, and habitability of remote exoplanets. Every new data point brings us one step closer to answering one of humanity's greatest questions: are we alone in the universe? The revelation of Proxima Centauri B's unique characteristics could represent only the beginning of a revolutionary shift in our approach to extraterrestrial research. Being the closest known stellar neighbor to our own solar system, Proxima Centauri b has long been a focus of rigorous scientific study, yet until now tangible evidence of alien life, such as possible artificial light or indicators of intelligent infrastructure, remained purely speculative.